can we support declarative abstraction for some subset of each applications in each domain? Okay. And that brings the question, what is the difference between declarative and imperative constructs? Those of you who've done programming languages with me probably know the answer very well, because this was an exam question. But I'll be interested particularly to know from others what you think is the difference, because this is a concept that we hear about since CS1 actually. What are some examples of declarative and imperative constructs that you might have seen in various courses you've taken? And specific to this course, when we talked of concurrency, which I've spelled wrong here, we saw some declarative constructs and some imperative constructs. So can you name those? Can you figure out what they were? Okay, so let me throw all three questions at you, and hopefully one or more of them you have some idea of how to answer. Okay, declarative versus imperative. So sometimes they complement each other. Okay, we talked about the array example. So you can declare an array, that's a type declaration, that's declarative, that's why we say declaration. And whenever you involve statements, things that work on data structures, then that's imperative. Okay, so a loop is imperative. So declarative specify what we want, as Jason said. And so we want an array, we don't care how it's implemented. The array here could be implemented in this way, where each element follows the previous element. Or you can put some gaps in there. Okay. Now that may not be very efficient from a locality point of view, and locality is something that's going to be important very much in high performance computing. But you didn't have control over what happens. You're hoping that the compiler writer did the right thing. Okay. Whereas in assembly language, you'd have to be allocating the various elements as separate words yourself, and you might actually put gaps or not put gaps. Okay. So locality relevant to HPC abstraction later, and we're going to study about that. So imperative, implement what we want. So here we have a sum that we've actually controlled ourselves. Okay. So now imperative can be procedural, functional, object-oriented. So you mentioned that Haskell is declarative. Not really, it's functional, but it's still imperative. You have to write functions. You have to go and say, compute this value, then compute this value, and there is an order when I go and give 5 arguments to a function, and each of these arguments themselves is a function. There's a particular order in which those arguments have to be evaluated. Okay, so there's definitely, when you do a conditional, there's an order in which the conditions are evaluated. Okay, so you are actually specifying how things should happen. Okay, whereas in Prolog, you just give a bunch of rules, and it just tries out the rules, all combinations of rules in different orders till it gets something right. And that's when it declares success. So Prolog is declarative. And this is something that you should have actually learned in your 455 class, the automata theory class, theory of computation class. So we can give a regular expression, or we can create a finite state automata. Okay, finite state automata says, if you're in this state, this thing happens, go to this state. It's very procedural or imperative. Okay, sometimes procedural and imperative are used synonymously. Declarative is you give a regular expression, pray that it's right. Okay, and some finite state automata is processing that automatically. Okay, so here we have competing. We can do the same problem using either declarative mechanisms or using procedural mechanisms. Whereas previously I gave you 2 sets of constructs that complement each other. Okay, they can both be working together to solve your problem. And by the way, state machines are very important. I'm mentioning this because that's something you all studied, but also this is very important in distributed computing. Okay, when we talk of consistency algorithms, they're often state machines. Okay, so we'll study an algorithm called Paxos, and you'll see that even more so. And declarative versus imperative in concurrency, well, we saw that synchronized, as I mentioned, that's just a keyword. You say, I want a critical section, and you get it. Those of you who've done operating systems, you've probably implemented that using semaphores, which is procedural. Okay, so or test and set instructions, so that's procedural, whereas in Java is synchronized. And but the wait call, that's a statement, okay, which happens, and there's an order in which that whenever there's statements, there's an order, and at least in imperative language, in procedural languages, in functional languages, there's no order. In some of them, and so notify and wait are procedural. Okay, creating a thread is procedural. So everything was procedural in Java except for this synchronized method, okay, the critical section, which is also a form of synchronization. Okay. So this is Java, and like I said, we are not taking a mechanism-oriented view right now. We're taking a problem-oriented view. So let's go and focus on some domain of problems and say, can we improve on Java somehow, given this set of problems? Okay, and we've seen how we could maybe have no programming at all and have a parallelizing compiler, and that will only take us so far. So can we have either pure declarative constructs or more declarative than Java? Okay, Java has got synchronized method in it, so it's not completely procedural for imperative for concurrency. So can we have something that's more declarative? And let's start off by being really ambitious. Okay, we'll really narrow down the set of problems so that we can be so ambitious, and say let's have pure declarative concurrency constructs. That means everything, thread creation, thread critical regions, thread synchronization, which is basically coordination beyond critical sections. Let all of them be declarative. Okay. So let's take an example of such an application. So often people go and print hello world in this class of applications. But why would you want to print hello world? Firstly, it's never clear to me why you want to print hello world in any application. My research area is distributed collaboration, where the same program can be used by multiple users. There it makes sense, because there are 5 users and I might want to say hello world. But when there's only 1 user, what's the world, right? Maybe hello. So, but hello world is kind of boring. So let's go and rather than that, print out a random number. If you're going to print out something, you want to demonstrate print out, let's go and do random number. So let's say I want 2 random numbers to be printed out. Okay? And I want this task to be done concurrently. So this is the desired output. I want 2 random numbers between 0 and 1. I want it done concurrently. And I don't want to do new thread, and, as in Java, and start and run and so forth. So the question is, think as abstraction designer. Think about what is the minimum you need, somebody would have to say declaratively to get this program working. Imagine you are designing an abstraction and you're saying for this particular problem, it's not random, it could be hello world or random, okay? But for this kind of application, we try to figure out what the kind is. You have 2 independent statements more or less. The seed is shared, but otherwise they're independent. I want to say 2 threads should go and do the prints rather than 1 thread. So 2 threads should do a statement rather than 1 thread. That's what I want to say. So what might you want to, so I do want to use some imperative language to go and say print. But this is concurrency unaware code. So now I have to add some declarative concurrency aware code, and I'm saying what might you go and say in this question mark box that gets a desired job, given that what you state there cannot know what a random number is. So it has to be more general than random number. And what might you want to put there? That's the question that was essentially answered by the set of primitives I'm going to show you next. Okay, and if you think a little bit, you'll converge to what has been invented. Okay, so this is something. This is not the COMP that John Ray saw. This is Java OMP. Okay, so what we put a special comment. Okay, and we're not just saying two because two what? So rather than saying two threads, we are saying let's go a little bit more verbose. Okay, OMP. This is an OMP directive. Okay, this is an OMP comment. Okay, so you want to distinguish this comment from other comments. So we are piggybacking on top of comments, and we are saying do it in parallel first, and then we are saying not only do I want you to do it in parallel, but I want you to go and use the following number of threads, and we are saying number of threads is 2. Okay, so pretty much what you guys came up with is what exists in this OpenMP standard. Okay, so let's talk about OpenMP. So this is called this is a declarative concurrency specification, and since it's a comment or it's something that's added on to regular code, it's also called a pragma or a directive. Okay, the word pragma I first heard in the context of the language Ada. Okay, which I mentioned to you guys a few times before. I think I mentioned Mesa to you guys. Okay, that was done around 78 or so, and I mentioned this operating system that did everything, that distributed services transparently. So that was also built from Xerox, as was Mesa, and Mesa got followed by Cedar, and Mesa inspired this language Ada. Okay, Ada is a language that's still being used by the military. Okay, and it had pragmas, and pragmas were directed to the compiler saying, here's a suggestion on how to improve performance. You don't have to follow it, but by the way, this is what I feel you could do. Okay, so the word pragma is something I believe was invented in Ada, and is being used as a term here also. Okay, so what is OpenMP? It's quote unquote language independent. The syntax that I showed you here is not the syntax that John Ray has seen before, but it's similar. So standard implementations exist for C, C++, and Fortran. Okay, so you're seeing here the same thing done through C. You say you say # rather than special comment, and you say pragma, OMP, parallel, num threads 2. So it's very similar. In Fortran, you would do something else. Okay, but very similar. So the standard implementations don't exist for Java, except there's some academic in Europe had an undergrad student. Okay, so if you guys think that I'm hard, think about this particular school. And this undergrad student implemented the OpenMP standard for Java. Okay, and this is the code I'm going to use in my parallel examples. Okay, I don't recommend you use it because the student had to graduate at some point and didn't do all of OpenMP. Okay, and there's a few bugs too that I've talked to his advisor about, but it's pretty good. Okay, and the idea is, if you've seen Java annotations like @override and other annotations, you'll be seeing more annotations in your next assignment 4. It's decorating some piece of code. Okay, annotations decorate classes and methods. This can decorate any statement or statement block. Okay. And what's important is not the exact syntax, but the attributes that are there. So they basically, these directives are assigning values to certain attributes used by the underlying concurrency system. Okay. And parallel is an attribute, which is Boolean. You either do it something parallel or you don't do parallel. If you're doing something in parallel, you can specify the number of threads as an int. Okay. And why is this more problem oriented? Because the syntax is closer to the problem domain. Okay, just as when you study functional languages, a recursive, or even in imperative language, or even in procedural languages, a recursive solution is much closer to the problem definition than an iterative solution. Okay, if you think of factorial, the only way you can specify factorial precisely is using induction, and then inductive steps directly translate into recursive steps. Okay, so but not every kind of statement can be associated with every set of attributes, and it'll be nice if the system could figure out that, look, these attributes don't apply to the statement, but because of the halting problem, you can't quite figure out what a statement does. So that's a danger here, that you might just specify certain attributes that are not relevant to a certain statement. Okay. So when we study, even though I'm going to be using OMP4 syntax, what's important is the set of attributes and values. Okay. So this is a table that we're going to fill gradually. We currently know of 2 attributes, and we're going to gradually, we can try to understand what these attributes really mean, how they're implemented, and then we'll go and expand the set of attributes gradually. Okay, and by doing so, we'll understand the problem better, and hopefully understand concurrency a little bit better too. Okay, so that's why I kind of want to do this stuff before your exam, because you'll really get to understand concurrency, which is a subject of the exam, a little better, having seen things using a different syntax. Okay. So let's take this undergrad thesis. I'm not going to ask you guys to implement the thesis, but let's go and get from you how you might have done the implementation yourself, just overall algorithm. And the first thing to answer, if you're going to look at that algorithm, is this is Java, and yet it's not Java. So the non-Java part is this special comment. So what kind of code do you think would process this comment? What would you call it, or what would it do? Where would it come in the Java code creation process? And this is a term that you might have heard before, that you might not have heard before. If you haven't heard it before, you can try to be creative. So what kind of program is going to process this, given that we are extending an existing language, Java, with an existing compiler and interpreter, okay, and virtual machine? So what kind of program would be processing these PRAGMAS? So we will use a precompiler approach. Yes, indeed, it's a preprocessor. Okay, and a processor of any piece of source code we'll call a precompiler. Okay. So in general, what does a precompiler do? Especially a precompiler for concurrent language. So it's going to take a source program. So the whole idea is that it's going to go and create. What does a compiler do? A compiler goes and takes a source program and converts that into object code, right? A precompiler will take source code and convert that into source code. Okay? That is going to be actually processed by the real compiler. So the preprocessor is going to take source code and convert that into source code. So now it's going to convert that into source code. In our case, that created source code better know how to do concurrency. So the source code is creating better be concurrency aware. It better be in a language that's concurrency aware. So Java is concurrency aware, right? It's got threads and so forth. So it's going to convert these comments into something that gets translated into a Java construct for concurrency. Okay. So now the precompiler can take in general, it can take a program that's language that's totally concurrency unaware. So you can take C, for instance. Okay, assumes that C has got no concurrency awareness. You can build a precompiler that converts a C program into a Java program. Okay, where Java is concurrency aware. So I know people, and one of my, in fact, those of you who've done 524, before I taught 524, the textbook we used was written by a guy called Michael Scott, who happened to be my office mate at Madison when I was a grad student. And he had done a language where he actually converted from one language to another language. His compiler was a precompiler like this, from one language to another language. So so it can take a concurrency-aware native language, and you can imagine a concurrency-aware new language like OMP. Okay, and now we've got a new language precompiler that goes and converts the program into some source program in a concurrency-aware native language. Okay, so I can imagine taking C plus the C PRAGMAS, converting that into Java. I can imagine doing that. Nobody does that. Okay, or I can just convert it into Java, which is concurrency-aware anyway. Okay, and that goes to a native language compiler, and now you have concurrency program in concurrency-aware imperative language. Okay, a compiled program, and then you might also have an interpreter as in Java. Okay, so this is in the translation process. That's the role that our precompiler will play. Okay, so that's the approach that was used by this undergrad student. Okay, so here's exactly how what goes on in terms of instructions. You say OMP4J minus S, and you give it this random program with the annotation with the pragma, and it converts random.java into a new random.java where those comments have been expanded. Okay, and then you can say Java C, that new random.java. Okay, and then you can say Java random. Okay, so that's how this system works. Okay. So that's what he's doing in this particular system. That he's actually working with Java. So the next question is, put yourself in his shoes and say, okay, we've decided to use a precompiler approach. What will this directive get translated into? This is a good test of how much you guys know threads. Okay, so given that I've told you everything, that I can tell you about threads in Java. Okay, and with that knowledge, if I was to tell you, here's a final exam, you have 2 weeks to do this, and go and take a take-home assignment and write this Java precompiler, where would you begin? What would you do? Okay, and or I just ask you an exam question. Here's this comment, expand it out. Don't have to write the code to do so, but tell me what your code should really expand to. Okay, so that's the question next. What would the general algorithm be based on this example? And this example is actually simpler than what I'm going to present incrementally. So just think of this example. How would you go and precompile it? And then later we'll think about how to do more complicated examples. Okay, so what's the general algorithm? We'll build on the joiner abstraction as David suggested, and not quite the barrier, which was close. And we'll assume there's a finish and join methods, though we could just work with notify and wait directly too. Okay, because you guys have seen in A1 that you can implement this abstraction using that. And we'll put the parallelized statement block in a runnable method of a runnable class, right? And that runnable method will do a finish call on the global joiner object, right? An object that is global to both the forking thread, the creating thread, the original thread and the created threads. Okay, and we'll have to create n instances of the thread object for each thread that we want to create. Okay, if we have n threads here, and each of them will be passed a new instance of this runnable class we've created. Right? We will then start the threads. We meaning the creating thread, and then it will go and do a join on the global joiner. Right? So what we did in A2, the joiner abstraction, is being directly used here. Okay. So let us now go and complicate matters. Here, this print line math.random accesses no variable at all. Okay. Nolan's breathing heavily now. If you ever done lambda expressions, you know what's coming, kind of. So what if I was doing a global plus plus, where global is a variable declared in the class that is being parallelized? So this statement occurs in some class that might have instance variables, static variables, and we are trying to parallelize arbitrary statements. And I want to go and say, OMP parallel thread num. Okay. And for now, forget about synchronization. Assume that we'll just live dangerously. Okay. Just tell me how I can parallelize and make sure that both threads change the same global. Okay. So that's the next question. How do we give runnable class access to global variables in parallelized class? Okay, so we're creating a new class, a runnable class. We're creating that class from code in this class that we want to parallelize. Okay, and how do we make sure that these two classes share globals? Okay, global variables. So as some of you suggested, we can just go and copy them into the runnable class. But as Nolan mentioned, you can have something called an inner class. So I can have declare a class C2 within the class C1, and all the code in class C2 can access the global variables of C1. Okay. So my modification is we let the runnable class be inner to the parallelized class containing the attributed parallelized statement. Okay. And now I will go to the next situation, and that's where we'll use the solutions that you guys presented. And we'll do this next time. Okay. So, but that's when this particular what you suggested would come into play. Okay. Okay, so last time we looked at a new way to do concurrency, which is declarative. That means we just give declarations, we specify what we want, the how is all magic. And we also try to see how the what could get translated into the how based on what we know about threads. So, or at least we saw part of that. We took first a simple example where we have to go and print out in parallel random numbers, and there's no variables being accessed here explicitly. There is a random seed that we don't have to worry about, and which is in the math library, so we don't have to worry about it here. And we saw that the general implementation used our joiner abstraction. Our joiner abstraction is built on top of wait and notify, so one could use wait and notify directly or some other abstraction. In fact, the actual solution we'll see uses another abstraction. And the whole idea was that we want to parallelize a piece of code that can occur in a method or may not occur in a method. It is some statement. And if we have to use Java, we have to go and put our parallelized code into a method called the run method, which has to be put into a class, which in turn has to implement the runnable interface. So we go and wrap this code into this method and class. Okay, and then if you have to create n threads, we create our declarative primitive says n threads. We create n thread objects in Java, and each of them we pass an instance of that class. Okay, so that's what we saw. And then we said, what happens if we do global variables? And global variables are easier than the next set of variables I'll talk about. So the solution we saw involved inner classes, but John Ray mentioned a more complicated solution which would work for our next problem, and we'll look at that later. So the whole idea is that a class can be declared inside another class, and I personally don't even mention this in my 401 class, because now that class is not visible outside and it's not reusable, and I like reusable code, but people have problems going to the Eclipse menu and and saying new class. And so people often use inner classes for that reason. And they use inner classes also, and this is a good reason to use inner classes, so that because the inner classes can access the variables in the outer class. Okay. Now maybe that's not a good reason either. Maybe you should have getters and setters instead, but certainly convenient. So what we'll do is what we did was we had the statement that we want to parallelize inside some class, which we'll call the parallelized class, and then we created another class called the runnable class that wraps the statement. So now we'll make the runnable class be an inner class of the parallelized class. So the runnable class can access all the global variables in the parallelized class. Okay, so that's where we ended last time. And the complicated solution we saw from John Ray wasn't required, but now it's going to be required. So this is a very long variable name, and it may be a little confusing. So what we have is a variable that is not global. Okay, so an inner class can access the global variables of the outer class, but it can't access variables in the stack. And we have a stack variable, so it's not global, and that variable is not inside the statement to be parallelized. It's not declared inside it. It's referenced inside it, but it's not declared inside it. So when we wrap the parallelized code into the method and a class, the declaration of this method of this variable will not occur in that method and class. The declaration exists in this enclosing block. Okay, so this is where we have to do the copying approach that John Ray mentioned last time. Okay, so what we'll do is, and this what we're going to do is, so how do we give runnable class access to variables that are not global and also not declared in the attributed parallelized statement? That's the question. Okay, and for those of you who've done 524 with me, we saw that there are reference parameters and there are non-reference parameters. And if we had reference parameters, John Ray's solution would work just fine. But we don't have reference parameters in some languages, in particular Java. In some languages, you have value result or copy in, copy out parameters. And if you don't quite know what this means, look up Wikipedia. But we'll use that concept here, basic concept, and you'll see that concept being used here. So what we'll do is for each non-statement and non-global variable that is accessed by the parallelized attributed statement, we'll create a global variable. Okay, and we'll go and before we execute the parallelized statement, we'll copy the non-statement, non-global variable into this global variable. We will take that parallelized statement and replace all occurrences of this non-statement, non-global variables with the global variables. Okay, so they reference the global variables now. And then we'll copy the values. So, and then we'll go and execute the method in parallel. And now this shared variable has been updated. But it's not the variable that initially occurred in the code. So we'll go and copy the values back into the original variables. Okay, so we have some original variables that we can't access directly. We'll create some new variables that will contain copies of that, and that will be global variables. The original variables are substituted by the global variables in the statement that is in the parallelized class. And the parallelized class accesses that substituted variables, and then we copy the values back. Okay, which is what happens in copy in and copy out parameter passing, for those of you who do know that. Okay. So that's the idea. And I'll let you guys now look at the actual code generated by the undergrad student who did OMP4 for that parallelized declarative construct. And given, I've told you the basic concepts in parallelizing it. So I'll let you guys, he uses a certain library whose function you can deduce based on the argument we've given so far. So I'll let you guys try to interpret this code, and then we'll go and do some more interpretation if needed. Okay, so just look at this code, try to understand what it's doing, and map that to the algorithm we we just talked about. So what's going on? Here's our original variable, which is neither a global or local to the statement. And here's our shadow variables. And these shadow variables are in a particular class. And we create an instance of the class. Okay. And we define the variable to be public. And we define it to be public because who's going to see this code? Nobody's seeing this code. Okay. So public variables are dangerous when somebody can see the code. And this is all hidden. Otherwise, you're going to define getters and setters. And before we do any creation of threads, we go and copy the original variables to the shadow variables, global variables. And here's our runnable class, an inner class. Okay, and it's an inner unnamed class. This is even, more extreme than just creating an inner class. So you just say, I want to create a new subclass of the interface runnable. Sorry, new implementation of the interface runnable. And you don't even name the class, it's an anonymous class. And you just go and provide the methods defined in runnable, and you just define the run method. Okay, so we are saying, here's the class, and we are going to just instantiate the class immediately after declaring the class, so we don't ever have to go and name the class. Okay, so this is not the most readable code, but it does work. And we are going to create two instances of this class. So that's what's going on here. And here's our the reference. Here's where we've taken the original variables and substituted them with the shadow variables in our code. Okay, so where the original code said local non-statement global plus plus, we are now saying OMP context dot local underscore non-statement not global. And here's our weight. Okay, and here's our creation. And what we do is we use a thread pool object. So we create this OMP executor object, which, so sorry, I shouldn't have said that's our join. Before that was our copying back. Okay, so after we execute this, we copied back. And now we're talking about how we actually doing the fork and join. So the fork and join are being done using this object called OMP executor. And fork is creation of the threads. So we don't say new thread, new runnable. We say OMP executor dot execute. Okay, and OMP executor is just this object, which is the thread pool. And we say execute this runnable. So it also uses runnable, but we don't say new thread. We just say execute in the thread pool. Okay, and then this is our join. Okay. Okay, so let me just back off a little bit. And what have we done? We took some OMP constructs and showed that they can be implemented using constructs that we've already seen in Java and which you've used. Okay, so basically what we've done is we've compared two sets of abstractions and asked the question, can one set of abstraction implement another set of abstractions? Okay, so can A1 implement A2? And we see this kind of, and a question like this tells us something about the expressibility of abstractions. Okay, some abstractions are more expressible than others. They can do more sets of problems they can do more problems than others. And we've seen that some abstractions can't do all the problems we might think of. Okay, so a Turing machine can do all the problems we can think of, but regular expressions can't be describe all kinds of problems. But if you just compare regular expressions, one abstraction, which is declarative, with finite state automata, which is procedural, so we see that we can reduce one to the other and vice versa. Okay, this is something you studied in your 455 course. And we've seen also that sometimes the direction goes one way. Okay, And what we've done is for concurrency answered a similar question, that given threads and wait and notify, can we implement OMP parallel? And we've seen that we can do it this way. Okay, so this is generally this idea is more general than what I just talked about. And I might often ask you that can you simulate abstraction A with abstraction B? Okay, so if those of you who've done operating systems, one of my favorite operating system questions is, can you implement semaphores using monitors? Okay, that's a fun question to ask. A not so fun question to ask is, can you implement monitors using semaphores? Okay, which gets much more messy. So it's good to sort of know the expressibility of different kinds of abstractions. Okay, so when we are looking at abstractions, we want to look at performance, we can look at ease of programming. We want to look at, of course, expressibility, but we want to also look at things like performance and ease of programming. And how do you measure ease of programming? We talk of this language versus that language, and people get into these debates, and these become really religious wars often. And ultimately, what you should really be, and what's a good measure? Well, you can say amount of code. Okay, that's an easy measure. When I did my thesis, that's how I defended the abstractions I created. Today, people say, oh, we're going to have studies, okay, which is much more in-depth answer. And compare, go and give two sets of abstractions to the same sort of programmers and see how well, how much time they take, what they think about the abstractions, how many errors the code has. Okay, so usually involves experimental data and arguments rather than proofs. Okay. So if I want to argue for ease of programming, I should really be giving you results of experimental data and these arguments. And there's not many people who do that, but there are some who do. And I'd like to argue that without these experiments, you can sometimes say these experiments aren't needed. Just believe my arguments. Okay. And if I want to tell you that the declarative non-parallel, the declarative parallel construct is easier to program than the equivalent procedural abstraction, you shouldn't debate that too much with me, right? Here I'm showing you what I have to write in the small box in the declarative fashion, and I'm showing you on the left what you have to do using procedural abstractions. And you probably will believe that, the declarative is easier to program, okay? And but even if I can't give you full experimental results, based on last time's class, I'm going to give you a case study to convince you why that might be better. And I say this as somebody who's not really programmed in OMP. Okay, I'm the typical academician. I love to talk about things I know nothing about, right? So I've never programmed in this, and so that makes it more fun to talk about it. But here's what happened last time. So there was a student who had done operating systems and had done P threads. So when he was having a lot of trouble with Java threads. So I said, well, tell me how a P thread works. And he said, and what's a P thread used for? I said, well, isn't P thread used for creating new processes? So, he'd forgotten. That was a while since he took the course. So I told him, no, that's the fork. Fork creates processes, and P threads. And by the way, I'm talking about P threads without ever having used P threads. Okay, so correct me if I'm saying anything wrong. Okay, but P threads are used for creating threads, and fork is used for creating processes. Okay, so he was confused about those two first. Then, of course, he had to look up the Java API to see how the threads worked. Okay, and he spent 2 days, and some of you, I believe, like Andrew, had the same problem in 524, confused thread.start with thread.run. Okay, and he took a while to figure that problem out. Okay. And so there was a long debug time. Okay, so this is my experimental result. Now here's the conjecture. So this is imperative constructs. Declarative, had he understood a C, PRAGMA, OMP, parallel, num threads to syntax, the syntax I show on the top, which is what you'd see in C, going from that to the bottom one, which is applicable to Java, doesn't seem that much of a jump. So the higher the abstraction, the less code you write, and if the abstraction is tied to a particular language, the same abstraction implemented in different languages would have similar, the syntax would be similar, the primitives would be similar. So that's the argument for declarative. Having said that, I do run into problems, maybe because I did 455 a long time ago. I do run into problems when creating regular expressions. And I often have to use the debugger on the web to see whether my regular expression is right or not. So sometimes just writing code and debugging it using debugger is easier. And that's one problem, by the way, with declarative abstractions. You can't debug them using a debugger. So I'm just sort of making an argument for both sides. Okay, so let's back off again and say, what have we seen? I've gone and motivated declarative abstractions. And then the question becomes, how far can we go with declarative abstractions? Okay, and we saw that we can do this printing of the random number using a declarative construct. Okay, so let's try to complicate our problems to see whether we need more declarative abstractions. Okay, so what did we do? We had system.out.println math.random. Now that you've sort of done your assignments, you've seen that my way of printing is, I always suggest that you don't use print directly, you use tracing. Okay, so I'm going to put a trace method in here rather than print. Okay, and let's go and here's my trace. It's going to print the current thread. Then it's going to print what you want to trace, and then it's going to do a print line. Okay, and if I do that, I would like to see this. Okay, I would like to see the two random numbers, and also I would like to see the threads that printed out the two random numbers. Okay, that's what I would like to see, but what I see is this. Okay, so I see intermixed output in my solution. And the question is, why do you see that? And I know at least one student who should be giving the answer immediately, but I'll just take a pause here. So printline is not thread safe. Okay, so you have two threads printing to the same object, and and the characters get intermixed. Okay, so you can solve the problem by using a synchronized statement. You can say synchronize this, and that would solve the problem in Java. Okay, and you can synchronize this with the OMP construct. Okay, we know how the OMP construct gets translated, and the OMP construct just goes and puts this into a runnable method, and the runnable method is free to do synchronize this. Okay, but then we would like to go and have as much declarative as possible, so we can, instead of doing this, do this. So, and this again becomes more language independent. So certain languages don't have objects, don't have the notion of this. The parallelized code might be in a static method. So synchronize this doesn't make sense. You'd have to say synchronize on some object you have to choose. So you just say OMP critical. Okay, I told you guys the synchronized methods basically implement a critical region. So you're saying, look, this particular region. So what you parallelize may not all of it might be critical. Okay, only if all of it is critical, then what's the point of parallelizing? It's going to happen sequentially. So some sub part of the statement that you parallelized can be made critical. Okay, in which case, essentially the synchronize, in Java, this would get translated into synchronize this. Okay, so that answers your question about how do you do synchronization. Okay, so what we're doing really is not so much looking at the Java syntax, but looking at the OMP attributes and their values. Okay, so these attributes are language independent. We saw there was a parallel attribute, there was a number of threads attribute, and now we have a critical attribute, and it makes the threads execute, the automatically generated threads execute the attributed statement atomically. Okay, so far, what we've done is take our complete program is parallelizable. Okay, we could have actually run the program as independent processes. So in general, you create threads when some parts of the program process have to be parallelized by one set of threads, and other parts have to be parallelized by other set of threads, and some of these sets might have only one thread. Okay, so let's try to create a serial plus parallel. So I'm going to now have the trace statement not only in my OMP parallel construct, but also before it and after it. Okay, so I say trace forking, I do this parallel construct, within the parallel I do some critical code, and then I say trace joined. Okay. So what do you think, given that threads go and print out, given that trace statements print out threads, what do you think will be output now? Which thread will be printing out fork and join? We have two threads here, thread 2.5 and thread 1.5, both in pool 1. And which thread will be printing out forking and joining? So if I do this, it will be the main thread. Okay, this is my complete program. So the main thread will print forking and joined. Okay, and I use the word forking and join because I am, and so this is what's going on abstractly. This fork join abstraction is much more general than OMP. Okay, and what does fork do? Fork basically goes, you go and say fork n times some statement. Okay, so that's a general idea. So you're given a statement and you say fork, and before that, and you do join before that. And the semantics are that some thread T0 executes fork. When you do fork n, T1 to Tn threads are created to execute the statement. And when they finish execution, and then T0 joins, and the join succeeds when T1 to Tn finish execution. Okay, this is not like a joiner abstraction where the threads execute a finished call and then can continue. No, join means wait for them to terminate. Okay, so this is, even though the word join is being used a little differently here. Okay, and then T0 continues on. Okay, so this is a general abstraction. So you create thread 1 to thread n, make each fork thread execute fork statement, make creating thread wait for termination of thread 1 to thread n, and that's what happens here. Can you think of an equivalent interpretation of fork join that is more resource scarce, that uses fewer resources? Okay, I'm saying this is a solution that you'll see often, but this is not the most efficient solution. It's easier to code, but it's not the most efficient solution in terms of resource usage. So as Randy mentioned, and as those of you who've done 524 with me have seen when you guys did eager evaluation, what we'll do is we'll not create n threads, we'll create n-1 threads and have the statement executed also by the T0, and then T0 goes. So we create thread 1 to thread n-1, make forking thread in each fork thread execute fork statement, make forking thread wait for termination of thread 1 to thread n-1. And this is not what was done in that piece of code we saw from the undergrad, and that's because it's a little messier to code, because now T0 has to, the statement has to be executed by two pieces of code, the creating thread and the created threads. Okay, so maybe if you have n is large, it doesn't make a difference, but if n is 2, it makes a difference. So those of you who've done operating systems and know something about Unix, I use the word fork join, and you guys have probably seen fork and join in operating systems. Okay, and so let's go and connect it to that, because we'll understand yet another abstraction based on what we've learned here. So Unix fork join had to do with processes, not with threads. Okay, so I told you earlier that this undergrad student was confusing process with threads, which is understandable because they're both schedulable units. And what you can do is you can do a fork in any Unix process, and whatever follows after fork, so some process P0 can do a fork, and whatever follows after fork is executed both by P0 and a new process P1 that's created by the fork. Okay, So this is executed both by P0 and P1. Okay. Very similar thing. And if you want the creating process and the created process to do different things, we can go and look at the return value of fork. And the return value in the parent, in the forking process, is a child PID. And in the created process is 0. Okay? So we can go and say, if child PID is not equal to 0, okay, we can put some piece of code, we can say join child PID. Okay, so the parent, if you're the parent, and you're the parent if the child PID doesn't return 0, and then you join. Okay, so we have a join call in Unix too, that allows you to go and wait for the termination of that process. Okay, so so this is Unix, and so this join is called executed only by P0, and it waits for termination of specified child process. And what if I want to create end children? How given these abstractions, how might or given these abstractions, maybe some variation of them, how could I do that? And especially those of you who run operating systems. So yes, indeed, we can put a loop there, and we can have a join with no arguments, which is easier, which just says wait for all the child processes to die. Okay, so it's keeping that internally. But indeed, we can store them in an array, or we can go and catch the children number 9 signal, which is a much more complicated solution. So we can just do a join. Okay, I believe this is what you can have a join without any PID. It's been a while since I programmed in Unix, which just says join for all children. Okay. Okay. So Unix did this in the 60s, late 60s. Okay, and OMP is late 90s. They got invented. So when I was teaching programming languages, I kept telling you guys how some classic concepts are now resurfacing as modern languages, and so this is anything that's classic and that continues on, is something worth studying. It's time tested, right? So so this is essentially what's happening in OMP parallel thread num n. Okay, it's a fork join. It's a very succinct way of saying fork join. An idea that was as old as Unix, and maybe there was something before Unix that did it, but as far as I know, Unix was the first system to do this, to have this. Okay, and you can again argue that, look, the declarative is much easier than the procedural. Okay, you can say that imperative code is arguably more error prone. I think I once saw a survey that wanted to know how many times do programs that do fork not go and have a join after them, or not check for the child PID. That means they just go and have the parent process and the child process do the same thing. And this is a survey I saw a long time ago, and they found one counterexample where the forking thread did the same thing as the fork thread, and that was a bug. Okay, so you do need to go and check the child PID. Whereas what we see here, there's no PID being checked explicitly here, at least. And by the way, if you want to do fork join in Java, of course you can implement the joiner object, but there is a version of join that you can use, which is more like the Unix join PID. So forking is basically creating a new thread. Okay, and you can take a thread and say thread.join. And basically what you do is you're saying, please block me till this thread terminates. Again, not quite like a joiner abstraction, okay? But it is something you can do. And fork join, I told you guys, existed in Unix in the 60s. I'm a big fan of this language, Mesa, I keep mentioning because I used it for my thesis. And it had, as far as I know, it was the first programming language that had fork join in it. Imperative. And then came OMP, which is declarative. Okay, it's just some history. Okay, so we are looking at, what is the range of declarative constructs we can have. And let's go a level up and try to, and what we're doing is we're looking at certain classes of problems, and we're gradually expanding the set of problems to motivate more declarative constructs. Okay, we began with just pure OMP parallel, then we went to critical, and then we understood how OMP parallels like fork join, and we're going to look at more declarative constructs too. But before I do that, let's just focus on the problems themselves, not declarative as a procedure, but just the problems themselves. Okay, that's kind of what I'm doing. I'm looking at, I'm focusing on problems. I'm taking the application-oriented viewpoint, and then going and saying, here are some abstractions that are right for this set of problems. And let's go and try to go and give names to these classes of problems too. Not, oh, I'm doing print line random, I'm going and doing tracing of random. Let's go and classify these problems into categories somehow. Okay, and there's many ways in which you can classify problems. And I'm going to say, when I'm printing hello world or printing a random number, I basically have the same code being executed with no shared data really. Well, maybe with print hello world, there's no shared data. Okay, so I can have two threads go and execute hello world, two different pieces of code, no shared data. And then when I do print random number, there's no explicit shared data, but there is some random seed that we are sharing. Okay, so I'll call that same code and same data. And random number printing in parallel seems kind of useless, just as printing hello world in parallel seems useless. That's something that doesn't take that much time. It takes much more time to create the thread than to go and print hello world. If you're printing a large file, of course, it might make sense. But you can also make more sense. A problem like this can make more sense, but the computation is hard. So maybe I convert the random number to first an integer and then try to figure out whether it's a prime number or not. Now things get prime numbers, to find out, determine if a number is prime or not takes computation. So maybe this is a much more interesting problem, okay, to do in this category. So we have here then two examples, printing out a large piece of text, here hello world, but maybe a very, very large piece of text that may take time, or printing out whether a random number is random or not, is prime or not. But it's kind of hard to come up with many more examples of this category, where it's the same code and same data or no data concurrency. Okay, so given the names, given how I've categorized this problem, same code, same data, can you use this nomenclature to go and come up with other categories? Okay, so what other categories does this kind of naming suggest? Okay, and so then we'll get maybe a nice taxonomy. Okay, so I told you guys I work in collaborative systems, and we have same time collaboration, different time collaboration, same space collaboration, different space collaboration. So you can have a matrix and say is the same time, same place, same time, different place, distributed, and so forth. So similarly here, as Jason mentioned, we can have same code or not same code, or we can have same data or not same data. Okay, so you get 4 combinations. Okay, so that's an easy categorization to derive. And let's go and think about real examples here. Okay, so we've seen same code, same data. Okay, print hello world, no data, which is like same data. The prime number example. What about same code, different data? And there's probably many examples that you can think of. Just to narrow your thinking, think of your A2. What would it mean to do same code, different data in A2? So we're doing token count or sum in parallel, and same code accessing different data parts. So we have this long list, and we go and create these children threads that do different parts of it, and then we go and combine the values later. Okay? So that's an example of same code but different data. How about same data, different code example? Or multiple data and different code example, again based on A2. So we might want to, if I'm given in your A2, 1, 1, 2, 2, 3, 3, I might want to sum the values up. Or I might want to figure out how many times 1 appears, how many times 2 appears, how many times 3 appears. So they may both be interesting problems, same data, but different code. Okay? And if I do each of these problems sequentially, then it's same data, different code. Now if I do the sum problem and the token problem in the same list, and the sum problem itself are divided into multiple threads, and the token counting problem also divided with multiple threads, then I have both combinations. Okay, so do parallel token and count sum in parallel. Okay, so we are understanding, and this is good. It's nice to have these primitives that you have gone and mastered, but to understand where these primitives are useful and how the kind of problems that they can be used for is even more useful sometimes. Okay, so we are understanding what we can do with concurrency and in an abstract way, what classes of problems we can do. So here's going to be my example, or different code, same data concurrency. So I've got a list, and I'm not doing a token count and sum of it. I'm doing a sum and a toString of the list. Okay, where I go and take the list and go and concatenate the toStrings of each element of the list. Okay, that's what I want to do. So I know how to do, so I know how to do same instructions, same data with OMP. So now my question is, how can I do this problem, different code but same data with OMP? Okay. So how to add alternation, okay, where the code does one thing or the other, how can I add that to OMP fork join? So how can I take the OMP fork join, and I'm allowed to extend this, and I can extend it using procedural primitives too. Okay. So I've gone and done, I want to use OMP parallel, but I do want to go and have the flexibility to do different things in different threads. Okay. And the hint is, think of Unix fork join. In Unix fork join, I was somehow able to go and do different things after fork. So what can I go and add to OMP to have the same flexibility? Okay, again, become language designers. I have the OMP parallel construct, I have the critical construct. I just want to add something to it so that I can do this problem in particular and do different code, same data concurrency in general. So Unix inspiration, as Randy mentioned, just as Unix does, we can go and find a thread ID and then use a thread ID to go and decide what to do, okay? Which is what we do in Unix. So T1 and T2 must start executing the same piece of code. Okay, that's how fork join works. But that code can then go and query and find out what the thread ID is, and if we create 2 threads, the code can say, am I thread 0? If so, I do the sum job, and if I'm 1, I do the toString. Okay, just as Unix did. So allow each member of the thread sequence declarative created to execute an imperative step to determine its index. And different code being executed accessed by different threads based on the index. And here's a piece of code that does that. So in OMP4, and similar construct occurs for C also, there is this variable that you can access. It's defined by OMP4, and you say OMP4 thread num equals 0, then do sum of rounded sum, or do toText. Okay, so we're still using the OMP parallel construct. Okay, and now we are coming nearer to Unix. So OMP4J thread num is a predefined runtime variable with a different value for each fork thread. So what we've done is that we have our declarative constructs with attributes, and what we've also done is now added some operations, some procedural abstraction, and we should get, there are two things we really want to know. We want to know how many threads were created and what is the thread num. Okay, they're both related things. So, so this facility exists in general in OMP. Okay, so now let's come to something more complicated, something similar to the kind of parallelism we did in A2. I want different data, different code, same data concurrency. Okay, so so that's what we had, and now I want same code, different data concurrency. So I want to now go and round up a float, let's say. Okay, and one thread rounds up some elements of the list, and another thread rounds up the other elements of the list. Okay, so I want different data but same code. Okay, and you guys have done this with in A2, but you've done it with arguably messy procedural constructs. And what we'd like to do is use some of the procedural constructs that OMP gives, but it's parallel declarative construct also. So we need to divide data among threads, and we need to create essentially a thread-aware round. Okay, so what we earlier did also was a thread-aware piece of code that checked the PID, and we want to create a thread-aware round. So what do we need? And this particular round is going to be looking at the thread ID, because we're going to have the threads are going to access different pieces of the data. So each thread, we're going to use thread ID to determine which piece of data to go and access. Okay, so we have the thread ID, which we can use to do different to access different parts. But what else do we need besides thread ID in this particular task? So I've got a list. That list has to be rounded. We're going to round it in some kind of loop using some index. Okay, and how would I go in? What are the parameters that this thread-aware code will use besides the PID to make sure that one thread accesses some elements of the list and the other thread accesses the other elements of the list? So we're going to do this based on the thread number, number of threads, and loop index. So that's the partitioning algorithm. So let's go and try to look at this concretely. So here's my single threaded round. I'm going through the list. I'm going and replacing the list element with a float object, a float value, and then I print out, I do a trace also. So I want to ask two questions. First, a simple question. Why use primitive float and not a float object? Okay. And the second question I want to ask is, what exactly should I write here to make this parallelized? Again, we kind of know what we have to do, but just tell me exactly what I need to write here to do the parallelized version. So let's answer the first question first. What would be the disadvantage of using a float object rather than a float value? So float versus float, is garbage collection issue. We also, as Randy mentioned, allocate more space. We have to go and create that space. It takes time, and garbage collection would be a real issue here. So as Eugene mentioned, we put a compound statement for the body and proceeded with the parallel pragma. body of loop is executed based on thread number, threads, and loop parameters. So each thread will execute only some iterations of the loop, and it'll go and say, is my thread number compatible with the loop index, given this being the number of threads and this being the total number of iterations. Okay. So we're going to assume there is some method called process iteration, and process iteration is going to be a partitioner, the kind of partitioner that you guys had, that will go and return a boolean based on whether the thread should process an iteration or not. So this is my code. I haven't given you process iteration here, but I'm just calling process iteration. So I go and say OMP parallel thread num, and I do that before the for and the trace. Okay, and that precedes the for. And in there I go and every thread goes and calls process iteration for each iteration. Okay, and if process iteration returns true, then it goes and executes the iteration, otherwise it doesn't execute the iteration. Okay, and then at the end we go and print out round. Every thread goes and prints out. So every thread prints says round started, and every thread prints out also round ended. Okay, and process iteration could just do many things. And different useful implementations of method, and maybe a factory chooses it, like as in A2. And UG mentioned basically doing a mod function to figure out, just go and divide it based on using a mod function. So thread 1 does 1, 3, 5, 7, and thread 2 does 2, 4, 6, 8 elements. Okay. So, and we could have used this partitioning mechanism also in A2. We used a more complicated one, but this might have been the easier one to do. Okay, this is what UG and Randy were suggesting, actually. So that's what's going on here. So what we've done so far is we've taken two problems, the round problem and the sum problem. And we've done them independently. Okay, so we can do either sum or the round. And what you might want to do is round up the list first, and then do sum and do text. Okay, so let's say I want pipeline functions. And I want to go and make this pipeline functions parallelize that. Okay, so let's go and do, and this is like I'm going to the situation that you guys were talking about, where we had both the sum and token count being done on the same list. Okay, so at the same list, and I do round first, then I go and find its sum, and then I do a toText. So there's really three operations being done, and I want to there's a precedence, there's a dependency here, right? Till the round is done, I shouldn't be doing either the sum or toText. But the sum and toText I can do in parallel. Okay? So I go and start with, let's say, numbers that all round up to 5, but they're different. So the round problem gets these numbers. It ends with all of them being 5. And then the sum of rounded should be 25. And the toText of rounded should be 5.0 concatenated 5.0. It's five times. Okay. This is single. And what I could do is have T1 and T2 do the rounding first. Okay. In parallel. T1 does rounding of some elements. T2 does rounding of some other elements. And then T3 and T4 can do the list sum and list to string in parallel. Right? And this is what's happening here. So I've got parallel round here first, which goes and creates 2 threads and does exactly what we talked about earlier. Okay. And then I've got separate thread team doing the second problem, where I go and say, okay, if I'm thread number 0, I do sum. If I'm thread number 1, I do toText. Okay, so this is just composing the two solutions we saw earlier. And this is separate thread teams. So what's a more resource efficient solution here? You could do pipeline. You could go and have this T1 and T2 first go and do the partitioning, and then they do the sum and toString in parallel. So rather than creating 4 threads, I'm creating 2 threads. Okay, this is like your problem, somewhat in A2. So let's try to code this. So we can remove the parallel construct from our round with process iteration, okay, because we're going to create the parallel somewhere else, okay, before calling round with process iteration. And I'm going to create the parallel here, and I'm going to go and say, hey, run round with process iteration. And then I'm going to go and say, if thread number 0, sum is this, else sum is toText is this. Okay, so I'm trying to use the same 2 threads to do both tasks, both sets of tasks. Okay, and so my parallel construct occurs before either of those 2 steps occurs. Okay. Can you guys see a problem with this? So if I do this, as Yuji mentioned, I can run into problems, okay, and see what's happening. My round starts, thread 1 starts a round, and it so the numbers to be rounded are all going to round to 5, and end up with sum of rounded to be not 25 but 24.95. Why did that happen? The second round ended. The second thread finishes its rounding before the sum is printed out. Okay, so thread 1 computes sum before thread 2 finishes rounding its part, which is what UT mentioned. So thread 1 finishes its rounding much before thread 2 finishes its rounding. So let's ask 2 questions. What kind of abstraction, which you have seen before, would solve this problem, and how would you make it declarative? Okay, so we're not going to, you don't have to implement a barrier like you guys had to. You're just going to write down OMP barrier. Okay, so you're saying, please, after round with process iteration, don't just proceed till my peers have also finished this task. Okay, and then we'll go and do this. And now you see that we get round ended, then we get round ended again, and then the other 2 operations occur. Okay, so this is why I wanted to do this before the exam, because it just sort of revises what you guys have learned already. Okay, and you see barrier at work here. By the way, as far as I know, the barrier construct is the most modern parallel construct that I presented so far. Like I told you, fork and join occurred in 78 or so, and the barrier occurred somewhere in the 80s, maybe after mid-80s. Okay, so that's it seems obvious right now, but just historically, it wasn't that obvious. Okay, and people used to implement similar concepts using lower level abstractions, but they didn't think of having this abstraction till later. Okay, so our list is growing. We have critical, we have barrier, we have those 2 constructs, so we are understanding OMP better and better. So the question is, what other declarative constructs do we need? So we have 3 minutes, and I think we can do this in 3 minutes. Yeah, it's nice to have this get thread number construct, but can you think of a parallel construct, a declarative construct that will get rid of this if statement, but yet give us the same flexibility? That we have two pieces of code being done by different threads. Imagine again, as a language designer, you're going to put a declarative construct there, and you're not going to put an if statement with thread number. And this construct, by the way, occurred maybe early 70s, so this was historically not that complicated. Okay, so we're going to have, as I said, just as there's a code block, these curly braces, when you say, here's a curly brace statement, S1, S2, S3, we are saying the same thread first executes S1, then executes S2, then executes S3. Now we're going to go and say, I want each statement to be mapped to a separate thread. Okay? And in the OMP way of saying that is, we say OMP sections first, and then for each part, like the switch statement arm Yuji was talking about, each arm of the switch statement, but there's no check there, gets executed by a different thread. Okay? And so the sections can be executed in parallel rather than sequentially. And I'm taking just 30 more seconds. So before there were curly braces, languages had the word begin and end. Okay, and you would say begin, statement 1, statement 2, statement n, and end. And the same thread would execute the statements in order. And there was a construct called co-begin, which said basically here are some statements, finite list of statements, and execute each statement in parallel, okay, and then wait for all, and then end when every statement has been executed. Okay, so a statement execution is statement section is executed by single rather than all threads. That's important. It's not that all threads execute this statement. Okay, in parallel, we put a statement, we create multiple threads also, but the statement is executed by all threads. Now also we create parallel threads, but we go in, all parallel threads have already been created by the parallel construct, and we just go and divide these threads among the different pieces of code. And in functional languages, where there is no state, you can take a sequential program that has begin and end and replace the begin and ends with co-begin, co-end, and it should still work. So that's why you see functional programming coming back in vogue, because high performance computing is becoming more important, and suddenly functional programming is becoming more important because it can allow more parallelism. Okay. So this is, you might have heard of Dijkstra. So he invented this in 1968, and Dijkstra is considered a very smart guy, and you guys couldn't quite come up with a construct with enough motivation, so he must be a really smart guy. Dijkstra's done many things. Okay, so we have gone and added section and sections to our list also, and it's getting bigger and bigger, and the time is getting later and later. So let's go and